We'll start with section 7.2 in this lecture. We'll learn about trigonometric integrals. So in order to evaluate the integral with the trigonometric functions, here are some basic trigonometric identities which we need to know. And here also some more identities where you have product of trigonometric terms like sine times cosine, sine times sine, or cosine times cosine. So these are 5 plus 3 8 important identities which we need to know and which we'll be using here in order to compute the integrals. So let's do this first example. Sine 5x times sine 4x. So if you go back to our list of identities, sine times cosine. So here, the first one on the right column. This is the identity which will be, I think it is sine times sine. So let's change this. Sine times sine will be the second identity. This one. 1/2 cosine A minus B minus cosine A plus B. So let's use this. So let me write that identity here. Sine A times sine B equals 1/2, open a big square bracket, cosine of A minus B minus cosine of A plus B. So here are the functions A and B. A is the angle 5x and B is the angle 4x. So let's apply the sine formula, sine times sine. So when we do that, we get 1/2 integration. The function will be cosine. We have to subtract the angle. The formula says A minus B. A is 5x, B is 4x, and then negative cosine A plus B. We have to add the angles 5x plus 4x and then close the bracket. Integral variable is dx. So 1/2 goes outside, which is the constant of integration. Then we have integral of, simplify this 5x and minus 4x, which is cosine x. Negative, simplify this 5x plus 4x, which is cosine 9x. And then we have a dx. So at this point, we use the formula integral cosine bx dx. Then we have sine bx divided by b. So we have 1/2 integrate this cosine x, we have sine x. Integrate cosine 9x, we have the formula on the right. Cosine bx is sine bx divided by b. So cosine 9x will be sine 9x divided by 9. The coefficient 9 comes in the denominator. And just bring down this negative sign. And for sure, because this is not a definite integral, you have to add a plus c. The next example, sine 7x times cosine to the 4 7x. If we want to use any one of these identities here, sine times cosine or sine times sine or cosine times cosine in the second list, you see we don't have exponents for the sine or cosine term. But here in this problem, we have an exponent for this cosine term. We have cosine to the 4 7x. So we'll not be able to use the exact identity listed there. So let's change a little bit. Let's try our substitution method. So u equals cosine 7x. So assuming the cosine 7x term is u, let me differentiate. I have du on the left. Differentiate the right hand side, dx on the right. So this is a default variable du dx for any assumption of a term called as u in the given problem, the u sub rule. Now let's differentiate cosine 7x. Differentiation of cosine is sine, and differentiate the 7x again, you have 7. differentiation of cosine, to be more particular, this is negative cosine. So write negative sine times 7. Now, if you carefully observe the given integral, all we have is a sine 7x here and a dx. That's these terms here, sine 7x and a dx. So keep this sine 7x dx on the right and move all the other terms on the right, which means you will divide by negative 7. As soon as you divide by negative 7, the terms look like this. Negative du divided by 7. Now, whatever you substituted, the function u, you call this as step 1, u equals cosine 7x, and call this as step 2, the substitution for 7 sine 7x dx. You say substitute 1 and 2 in the given integral. So the given integral is written as integral, you have cosine to the 4 7x. This cosine to the 4, which is cosine 7x, is u, so this becomes u to the 4. So you write u to the 4 sine times dx. Sine 7x times dx is negative du divided by 7. This is the replacement what we found. So negative 1/7 goes outside. You have u to the 4 du. Integrate, this becomes u to the 5 divided by 5 plus c, where u is the function what we assumed. So let me replace u is u is the cosine function. So this is cosine 7x exponent 5 divided by 5 plus c. Either you can do this, or at the same step you can change, you can write. If you don't want to plug in, you can write where u equal to cosine 7x. This was the substitution we made in the starting. So all you do is find the best substitution, derive it, plug in back to the given integral. Sine 7x cosine 4 7x was very messy, you could not integrate it. But rather, when we use the substitution, the problem reduces to a very simple integral, which is integration u to the 4 du. This is very simple and easy to integrate, rather than integrating sine 7 times cosine to the 4 7. So the best substitution makes the problem much easier. Next, we have a list of formulas. Suppose you have sine to the m, which means an exponent for the sine function, and cosine times cosine. There is no exponent for the cosine. You have to make a note. When you have such product terms, the plug-in substitution what you use is for the sine term, u equal to sine. See that we did not take our exponent m here in the plug-in. In the substitutions, you will not have the exponents. Whenever you have secant to the m times secant tan, take the secant tan as your substitution. U equal to secant x times tan x. I'm sorry, this I want you to take u equal to just secant. I'll tell you why you want to take u equal to secant as your substitution. If you take u equal to secant as your substitution, derive this du over dx. Derivation of secant is secant times tan. So this secant times tan you're seeing here. The plugin what you use is for secant, and the secant times tan you will find here after you plug in. So secant times secant with an exponent times secant tan, your plugin will be for secant. After you derive, secant tan will be there in the integral. The next one is cosine to the m sine x. So your plugin will be cosine x. When you differentiate, you will see sine x dx here. Cotangent m cosecant square x. Plugin will be for cotangent x. tan m secant square plugin is for tan. Cosecant to the exponent cosecant times cot plugin will be to cosecant. There is some similarity in the substitutions. If you carefully observe sine to the exponent m cosine x, cosine to the m sin x dx, these two are similar. So when you have a cosine x dx in the integral, your substitution will be sine. Whereas when you have a sine x dx in the integration, your substitution will be cosine. Because whatever you assume when you differentiate, you will get this dx term and the derivative back in your integrand. Integrand is the term which you integrate. Similarly, these two are similar. Derivative of tangent is secant square, derivative of cotangent is cosecant square. And you see that you have tan to the m cosecant square here. So if you assume tan x and say you derive this, derivative of tan x will be secant square x dx, which you are seeing here. Similarly, you assume u is cotangent, your derivative will be cosecant square x dx. So I purely want to write just the plugins here. So let me highlight the plugins, what you want to do here. This is u sin x, this is u cosine x, u tan x, u cosecant x, u cotangent x, u is secant x. So these are the plugins for these 6 type of integrals. Again, let me get back to the identity page, which was the first page. You cannot use any of the identities on this page or on the rightmost column, sine times cosine, sine times sine, cosine times cosine. The reason is you have exponents for either sine or cosine or tangent or cotangent or secant or cosecant. So when you have an exponent of the trigonometric term, you cannot use a direct identity but reduce the problem to the simplest integral you can. The next one is sine square 3x. So let me rename this angle 3x as angle A. Now I write sine square A equals 1 half 1 minus cosine 2A. So this is the formula I want to use, and here is that formula. Sine square x is 1 half 1 minus cosine 2x, the very first identity. Rather than x, I am going to write it as angle A here, which I wrote just now. Now I know the right identity I want to use for this problem. So let me replace this angle A by what we assumed. Angle A is 3x, so replace it, equal to 1 half 1 minus cosine 6x. Now that we have an identity for sine square 3x, let's go back, plug this in the given integrand. So the integral looks like this. This is 1 half integration 1 minus cosine 6x and then a dx. Now 1 half is a constant. Bring this out. You have 1 minus cosine 6x dx. Now integral of 1 dx is just x. Integral of cosine x 6x is sine 6x divided by 6 plus c. The next one is cosine to the 4x dx. Let me tell you some common error which students do this when they want to integrate the exponent function. They might do this cosine to the 4x dx. You see an exponent 4, you write it as cosine to the 5x divided by 5. Very fast and easy. You can do it in 1 second. All they do is this formula, x to the n dx. x to the n plus 1 divided by n plus 1. This is the integral formula for exponent. Suppose you have x to the 5, x to the 6 divided by 6. So you add 1 to this exponent 5, it becomes 6, the same exponent in the denominator. Well, you can do this formula if you have an algebraic term like this, x to the n, x to the 5. Yes, you're most welcome to do it. All these are correct. But if you have a trigonometric function cosine to the 4, easy to write cosine to the 5 divided by 5. But please understand that this is trigonometric term. This is not algebraic term. So don't do this formula, which is very easy and also very easy to lose the points. So make sure you understand what is the right formula in order to integrate cosine to the 4. Let me choose the cosine square formula. The reason is I will break this integral as cosine square x times cosine square x dx. If I break this as cosine square plus times cosine square, the formula I will use is this. Cosine square A equals 1 half 1 plus cosine 2a. In the previous problem, we used sine square A is 1 half 1 minus cosine 2a. Now I replace every angle A by angle x. So I have cosine square x equals 1 half 1 plus cosine 2x. So this is the formula which we will use here. So let me plug in. Each one of these integral cosine square function will be 1 half 1 plus cosine 2x. Again 1 half 1 plus cosine 2x times dx. Now 1 half times 1 half, which is 1/4, I'm going to bring it outside. And then I have 1 plus cosine times 1 plus cosine, the product terms, which is 1 plus 2 cosine 2x plus cosine square 2x. Now the first two terms are simple and easy to integrate. You have integration formulas for all this. But again, we don't have an integral formula for this cosine square. Easy to write cosine cube divided by 3 after integrating, but again understand the error. We cannot add the exponent by 1 and integrate like how we do for polynomials or algebraic functions. So we'll apply the identity again. For this term, I'm going to write it as 1 half 1 plus cosine 4x. The reason is I assume this angle 2x is your angle A. And it's exactly the same formula I've listed on the top. If I have a cosine square A, angle A, I have 1 half 1 plus cosine 2 times A. So if I have angle A is 2x, it doubles here, I have a 4x. So this is the identity which we had in our first list. We'll be using that. Now let me plug in this cosine square 2x formula and multiply out everything. So I have 1 plus 2 cosine 2x plus 1 half plus 1 half cosine 4x. And then I have a dx. This 1 half and 1 plus 1 half, these two terms, you can add and you can write it as 3 halves. And then you have 2 cosine 2x plus 1 half cosine 4x dx. Now you're good to integrate. 1/4, we're missing the integral sign here. So 1/4, 3 half dx integration is 3 half x plus 2 times cosine 2x integration is sine 2x divided by 2. Cosine 4x integration is sine 4x divided by 4. Now we can multiply this 1/4 to every term, and as soon as we finish integration, we write a plus c and multiply this 1/4 to every term here. So this is 3/8 x plus 1/4 sine 2x plus 1 over 32 sine 4x plus c. The next one is integration sine to the 5 2x dx. So let me break this integral as sine to the 4 2x times sine 2x. Now I rewrite this power 4 as a square terms and one more exponent square. Sine square and then one more square here. Sine times sine 2x. Now I use the formula for sine square 2x here, which means it's this formula, sine square theta equal to 1 minus cosine square theta. Now I replace theta is 2x, so sine square 2x is 1 minus cosine square 2x. So when I break like this and I plug in back this formula here, the equation becomes 1 minus cosine square 2x. Now I have a square times sine 2x. Now the best substitution to simplify this problem is carefully observe the pattern of terms. Suppose you assume u equal to cosine 2x and say you do the derivative. This is sine 2x times 2 dx with a negative sign. You're seeing exactly sine 2x dx here in the problem. So the best plugin will be u equals cosine 2x at this point. So use this plugin. So now I have simplified the sine to the 5 2x term like this, 1 minus cosine square 2x, the square sine times sine 2x. So let me rewrite. Integral sine to the 5 2x dx, the given problem, was rewritten as 1 minus cosine square 2x and one more square times sine 2x dx. And the best plugin what we have here is this one, cosine 2x is u. When I use this plugin, I will be able to rewrite the problem as integral 1 minus u square. I have one more square outside. And from this last line, I can rewrite sine 2x dx as negative 1 half du. So sine 2x dx is negative 1 half du. The negative 1 half go outside and you FOIL these 1 minus u square times square term, FOIL this and take this negative 1 half outside. So as soon as we FOIL, I have 1 minus 2u square plus u to the 4 du. Now I have negative 1 half. Integration of 1 is 1 du is just u. Integral of 2u square is 2u cube divided by 3. Integral of u to the 4 is u to the 5 divided by 5 plus c. Either you can plug in u was our assumption, which is cosine 2x, or in this step you can write where u equal to cosine 2x, what we assumed in the starting. Now the next problem, sine to the 4 times cosine cube, the angle here is 3x. Again, none of the direct identities work at this step because we have exponents for sine and cosine. So rather what we do is we'll break this integrand. Integrand means all these terms are called as integrand, and try to use a best substitution to reduce the problem in a way that we can integrate it. So let me write this as sine to the 4 3x. Cosine cube, I'm going to break it as cosine square 3x times cosine 3x and dx. Now you have cosine 3x dx. This is the term what we separated. If you want a cosine 3x dx, the possible substitution you want to choose is u equal to sine 3x. So as soon as you differentiate sine 3x, you have cosine 3x and dx. And you're seeing the term here. So the best plugin to evaluate this integral will be u equal to sine 3x, because the reason is you separated one cosine term separate. Now let me rewrite this cosine square 3x using this formula. If I have a cosine square a, the formula is 1 minus sine square a, the very first trigonometric identity. And now I'm going to write this angle a as 3x, which means this becomes cosine square 3x equal to 1 minus sine square 3x. So this is the plugin I will use for cosine square term. And I've already used u is our sine 3x, so this term will become u to the 4. So we have nice plugins for every term in the integrand. So let's rewrite the integrand. The first one is u to the 4. The second one becomes 1 minus u square. This term here is u, so this becomes u square. And then we have 1/3 dx. Also, when we differentiate sine, we have cosine 3. We also should differentiate 3x, so this becomes times 3. And when we divide by 3 on both the sides, this becomes 1/3 du equal to cosine 3x dx. So now we have 1/3 as the product term, which is a constant. This goes out. And multiply u to the 4 to both the terms. It is u to the 4 minus u to the 6. And then a d. No more dx, but all the variables are du. So make sure you write du, integral du. Now you are going to integrate this. This is 1/3 u to the 5 divided by 5 minus u7 divided by 7. And then you have a plus c. So make sure you write what is u sub in this problem. U was actually sine 3x. The next one is secant to the 4x dx. We will break this as secant square times secant square. And for each of these secant square, we'll use the formula 1 plus tangent square x. So if I use 1 plus tangent square x for both of these secant square, the problem becomes 1 plus tangent square x and then a square. And if you try to FOIL them, it's going to look very messy. So we'll not be able to evaluate this integral. So rather, what we do is we plug in for one secant square x and we keep the other secant square x for substitution. So now with all these substitutions, let me rewrite the given integral. The given integral becomes integral 1 plus tan square x. I use the plugin only for the first term. The second term becomes secant square x dx. I keep like that. Now let us try this plugin. Let us try u equal to tangent x for our substitution. The reason is when I differentiate tangent, I will get secant square x dx. And you're seeing that exact term here. So now let me go back and plug in this. So this will become 1 plus u square. Tangent is u. Secant square dx is du. Now integrate this. You have u plus u cube divided by 3 plus c. And this can be rewritten as tangent x plus tangent cube x divided by 3 plus c. The next one, you have tangent to the 4 times secant to the 4. Let me keep the first tangent the same. I'm not going to do anything with that. And let me break this secant as secant square times secant square. We can do that. A power 4 term is split as secant square times secant square. And the first secant square here, I will use this trigonometric identity 1 plus tan square x. Now the plugin what I use for this integral will be u equal to tangent x. The reason is when I differentiate, I have secant square x and a dx, and this is the term what you are seeing here, exact secant square x dx. So let's try to plug in all these. This becomes u to the 4 times 1 plus u square, and then this becomes du. How messy was the given integral, but when you use a right substitution, it looks way simple. Multiply this u to the 4 to both the terms, u to the 4 plus u to the 6, and then you have a du. Then you have u to the 5 divided by 5 plus u to the 7 divided by 7 plus c. Finally, you want to write where u was your plug-in tangent x. If you don't want to write where u equal to the right plug-in, you have to plug in and show the entire final answer in terms of tangent. The next example, tangent to the 5x times secant cube x. So let us split this power 5 as tan to the 4x times tangent x, and let us split the secant cube x as secant square x times secant x. When we split in this way, we want to still rewrite this in the next step. I will bring the tangent to the 4 in the front and secant square in the second place, and I want to group this tangent and secant. Tangent times secant in the last place, and then the dx comes. And now write the integral sign for every step. The reason for such a grouping is I want secant, tangent, and dx in one grouping. The reason is I choose a plugin u equal to secant x dx. If I choose u as my plugin and I start deriving this term, derivative of secant is secant tan and then a dx. And this is the term you are seeing here. And now I have a plugin for secant, which means this term can be written as u square. And if I want to use the same u plugin here, I want to rewrite this tangent to the 4. Let me write this as tan square x the square. And the formula for tan square x will be 1 plus secant square x, or let me change this a little bit. This will be secant square minus 1, and then I have a square. So when you use all this plugin, back the tan to the 4 term becomes u square minus 1 the square, and then times u square, and then times du. This is the simplest integral rather than the complicated integral with the tangent and cosines with exponent, where you cannot integrate them. Now FOIL this term, multiply u square, simplify. You have u to the 4 negative 2u square plus 1 times u square. Now multiply this u square to every term here, and this becomes u to the 6 minus 2u to the 4 plus u square, integral with respect to du. So integrate this, u to the 7 divided by 7, 2u to the 5 divided by 5, u cube divided by 3 plus c, the constant of integration, where u was secant x. That's what we assumed in the starting. The next problem is just secant x. So for this problem, the trick what we use here is multiply and divide the term by secant plus tan and secant plus tan. You will see in a minute like why did we choose this particular multiplication. Now let me rewrite the problem as secant x times secant plus tan divided by secant plus tan. We can multiply and divide by the same term. Still the problem will be the same. When you reduce it, you will have the previous step. Now multiply out the secant times secant, secant times tan. It looks like this. Secant square x plus secant tan divided by secant plus tan dx. Now try to use this substitution where we assume u is secant x plus tan x, the denominator. Differentiate this, du equal to, differentiate secant x, you get secant tan, differentiate tangent x, you have secant square x, and then a dx. If you carefully see, this is our numerator here. So you assume the denominator is u and you have the differential which is exactly the numerator. So replace these back in the above integral, du divided by u. Integral of du divided by u is natural log of u plus c. Where you want to write u is what you assumed, secant plus tangent. The next one is secant cube x dx. Break this as secant times secant square. Assume the differential term is secant and the integral term is secant square. So differentiate the secant term, all you have is secant tan. Integrate the secant square term, all you have is tangent term. Now you want to do the integration by parts, which means you multiply these two terms with a positive sign, and then you multiply these two terms with a negative sign and then integrate it. So let me write, the given integral is j, which means this will reappear. So I'm naming the integral as j. So write the integral secant cube x dx, this is the integral we want to evaluate, is secant times tan from the above table what we wrote, negative secant times tan square x dx. Now for this tangent x here, I'm going to use the identity secant square x minus 1. Now I will rewrite this secant x tan x negative integral secant x times secant square x minus 1 dx. Bring this down, secant square x dx. This will be the integral sign, so let me separate this. Now multiply this secant times secant square. This is secant cube. And rewrite the integral for this one, what we assumed in the starting. We rename the integral as integral j. Bring all the terms down, bring this down, secant x tan x. When you multiply this integral, you have secant cube x. And again multiply, you have secant x dx. This secant x dx here is your integral integral j. Now you're good to add a plus j on both the sides, separate the integral j. 2j will be secant x tan x. Integration of secant will be, this is negative times negative, this positive term. Integral of secant will be natural log secant plus tan, which was the exact previous problem where we derived the formula, plus c. J is the given integral we want to evaluate. So add one more step where we are dividing by 2 throughout. Let me add a page here. So you divide by 2 and the step becomes j equals secant tan divided by 2 plus natural log secant tan divided by 2 plus c. One more example. Cotangent square times cosecant square. So u equal to cotangent, this will be a plugin. Du equal to negative cosecant square, let me write CSC for cosecant, dx. So when I choose these plugins for the given integrand, it looks like this, u square and then a negative du. So negative goes out, u square du. Integrate again, u cube divided by 3 plus c. So this will be negative 1/3 cotangent cube. This was the plugin what we used in the starting plus c. So here in this section, we have learned different methods of integrating the trigonometric functions. For some of the examples, we have used the exact identity because the very first integrand which we wanted to integrate looks very simple and similar to the identities. But for the problems where we have exponents for these terms, suppose we have a sine to the 5 times cosine, say 2x, and 2x is the angle, will not be able to use this identity on the rightmost column. The reason is we have an exponent. For these type, we have discussed the suitable substitutions on page 4. So now we end this lecture on section 7.2.